So in the last lecture, we talked about the motion known as parallax, which is actually an apparent motion of background stars caused by the Earth's orbit around the Sun. However, of course, there are many stars and other astronomical objects that are in orbit that exhibit orbital motion, and we can observe some of these orbits and measure the basic properties of those orbits, like the period and size of the orbit. And we find that those two quantities in particular are related to each other in a way that was originally discovered by Kepler. But then we show that if we actually add our knowledge of physics into the mix via our laws of gravity, then that allows us to extract or unlock an extra piece of information, an actual physical property of the systems that we're looking at, namely their mass.
So Johannes Kepler, who lived from 1571 to 1630, came up with his laws by looking through the painstaking observations made by the astronomer Tycho Brahe, who lived from 1546 to 1601. Brahe made very, very careful observations of the motions of the known planets at the time. At the time, the known planets were Mercury through Jupiter. Kepler came up with his laws of motion between 1609 and 1619, and these laws improved upon Copernicus's laws of planetary motion, which Copernicus came up with about a century earlier. In 1687, Isaac Newton showed that Kepler's laws actually are a result of his own laws, Newton's laws, and the universal law of gravitation. So there are three laws that Kepler came up with. The first one simply states that the orbits of the planets are an ellipse with the Sun at one focus. This replaces one of Copernicus's laws that the orbits of the planets are circles with the Sun at the center. The second law is that the line joining a planet and the Sun sweeps out an equal area in an equal amount of time. One consequence of this, which we will discuss how to prove, is that planets' orbital speed is quicker when they are closer to the Sun.
The first and second of Kepler's laws are illustrated nicely in an animation on this website, which contains many astronomy animations relating to all aspects of astronomy and astrophysics. This is a collection of free resources associated with the Universe textbook. Kepler's first and second laws can be found here under chapter 4. So we see here that Kepler's first law, the fact that the orbit of the planets around the Sun is an ellipse with the Sun as one focus of the ellipse, is illustrated. And also Kepler's second law, which is often the trickiest of Kepler's laws for people to visualize and understand, that if you divide the orbit up into equal periods of time or equal time segments, then the triangle traced out by the segment of orbit traced out in that time and the lines joining the start and end of that segment to the Sun form triangles of equal area. That seems a little abstract. The important implication of this, which you can also see here, is that the further away the planet is from the Sun, the slower it travels. So you can see that in order for these triangles to always have the same area, when it's close to the Sun, it has to travel faster because it has to trace out a longer line segment to make up for the fact that the other sides of the triangle are shorter because you're closer to the Sun.
The third of Kepler's laws is that the square of the period of an orbit is proportional to the cube of the semi-major axis of the orbit. So p squared is proportional to a cubed. If we measure p in years and a in astronomical units, then the constant of proportionality turns out to be equal to 1, and the equation reads p squared is equal to a cubed. It's this third law that turns out to be particularly useful.
This relationship can be seen graphically here. If you plot the cube of the semi-major axis of the orbits of the planets versus the square of their orbital period, then they all fall exactly on a straight line as predicted or as found by Kepler's law. I should be careful with the language here. This is not a prediction of something. This is just, all Kepler did was figure out that this is the relationship the planets obey. Only when we add physics in do we find what it is that actually predicts this relationship. So let's add the physics in. And it wasn't too long after Kepler figured out his laws that Isaac Newton figured out the physics that underlies them. He came up, of course, with Newton's laws of motion and his universal law of gravitation. So Newton's laws of motion tell us or give us a prediction for how the motion of an object changes when a force acts on it. In the case of the planets orbiting the sun, for example, or stars orbiting each other, the particular force we're dealing with is gravity, and Newton also came up with a specific law to describe that specific force of gravity. It's Newton's universal law of gravitation. And when you put these two laws together, Newton's second law and Newton's law of gravitation, then these two laws predict Kepler's law here, that the total mass of the system times the period squared is proportional to the length of the semi-major axis cubed. And so it's adding physics in that allows us to get a handle on a new physical property of planets and stars that we otherwise wouldn't be able to measure. This, if we can now measure from our observations the period and the size of the orbit, we immediately get out the mass of the system.
Now, when you derive the third law from Newton's laws and his universal law of gravitation, then one can apply it not just to the orbits of planets, but to the orbits of any two objects about their common centre of mass. So, for example, the majority of stars are part of a binary system. So, in other words, stars usually come in pairs. Up here we have optical and X-ray images of the brightest star in the night sky, Sirius, which turns out to actually be two stars, Sirius A and Sirius B, Sirius A being the much brighter member of the system. But these two stars are orbiting each other. They are a binary system. And for the orbits of two stars like this, Kepler's law generalizes to the mass of star A plus the mass of star B times p squared is equal to a cubed. In this formula, once again, the period is measured in years, A is measured in astronomical units, and the two masses are measured in units of solar masses. So in other words, how many times the mass of our sun they are. On the top right here is a picture of the orbit of Sirius, of the Sirius system, taken over about a 50-year period. So just to give a quick example, we're going to do an order of magnitude estimate, so we're not going to use calculators, to estimate the mass, the total mass of the Sirius system, so the mass of Sirius A plus the mass of Sirius B, using Kepler's third law, this formula here. So from careful observation, we find that the period of the orbit of the system is 50.05 years, and that the semi-major axis of the orbit is about 1,838,667,445 miles. So if we just want to make a rough estimate, we can just approximate this to 2 billion miles. That's accurate to about 10%. One astronomical unit is about 94 million miles, which we can approximate to about 100 million miles. So given this approximation, the semi-major axis of the Sirius system, 2 billion miles, is about 20 astronomical units. That's 2 billion divided by 100 million. That's something you can do in your head without a calculator. Now, the period squared we can estimate to quite high accuracy, since the period is very close to 50 years. So p squared is 50 squared. That you can do in your head is 2,500. A cubed, A in astronomical units is 20. 20 cubed, again, you can do fairly easily in your head, is 8,000. And therefore, the mass of the Sirius system, which is just mass of A plus mass of B, is equal to a cubed divided by p squared from Kepler's third law. So that's approximately 8,000 over 2,500. And that's roughly 3 solar masses. So this example illustrates not just the use of Kepler's third law to estimate the mass of stellar systems, but also how easy it is to actually do order of magnitude estimates or rough estimates just by rounding numbers a little bit to the point where we can actually just use mental arithmetic. This is a vital skill in astronomy to develop. If you actually plug the numbers into a calculator, incidentally, then you'll get the actual answer is 3.09 solar masses. So by making these approximations, we've actually still come very, very close to the right answer.
I'd like to conclude by emphasizing this point again, that adding what we know about physics and interpreting astronomical observations through our physical theories allows us to measure physical properties of objects in the universe. This is what astrophysics is all about, understanding the physical properties of stars, galaxies, and so on.